We're in section 2.5, and so far we've covered substitution, direct substitution, simplification, and conjugation as methods of finding limits. Now this part is we're trying to find limits using squeeze theorem. So these are some of the prerequisites we need to explain the squeeze theorem. So first of all, limits of comparable functions. If f of x is less than or equal to g of x for values of x near a, then limits of f of x as x approaches a is less than or equal to limit of g of x as x approaches a, if both limit exist. So the fact that limit exists then will help us to actually have this defined and make the inequality sign for the limits also. Now what are we here's what it looks like. Look at point A, and for points around A, basically f of x is less than g of x, just an approximity of A. F of x is not always less than g of x, but for points near A, they are g of x is always bigger than f of x. And then all the limit points, if you look at limits as f of x approaches a, it's going to be right over here, and limit of g of x as x approaches a is going to be right there, and that one is bigger than this one. So this is the discussion of near, so you just choose some neighborhood around a and box everything, and in that neighborhood that the equality is correct. So what does squeeze theorem says? So squeeze theorem says if it gives a little bit more basically. If f of x is less than or equal to g of x less than or equal to h of x for values of x near a, and limits of f of x is equal to L as x approaches a, and limit of h of x is as x approaches a is equal to L, then limit of g of x as x approaches a exists and is equal to L basically. And so back in here we kind of showed if the two function, one is less than or equal to the other, the limits are less than or equal to the other, but both limits have to exist. This one is telling you a tiny bit more. It says if one function is squeezed between the two other ones, then and the two other ones, the outer functions have limits at a point as x approaches a, then the limit of the middle one exists and is equal to L. When is this good? When we're trying to discuss functions that, let's say, they are bounded, but they wiggle around a lot. That's basically one of the best way to find the limit for those type of functions. So this is h of x on top, and TL is the f of x, and then both of them as x approaches a, the y value for both of them is L. And the limits and they are both continuous, and the limits of both of them is L as x approaches a. Now we find another function that wiggles a lot around here, and I don't have any ways of finding the limits of that one. What do I do? If it's true that the other blue function is squeezed between the two other functions, the limit of that is going to be the same as the limit of those two other ones. And so basically, oh, and people talk about this as in walking a drunk to a door. Basically, it's going in and going, and you kind of have to converge to that door to get out. And so there's a lot of space, but that space right there is too small, so you know that you pass through that door. Basically, the limit happened. So the squeeze theorem is, if f is less than equal to g less than equal to h for values near a, and the limits of f of x as x approaches a is equal to L, and limits of h of x as x approaches a is equal to L, then the limit of g of x, the squeezed one, the sandwiched one in there, as x approaches a is equal to L also. So before trying to do one problem on this one, let's remember that sine of x is between -1 and 1, no matter what, and cosine of x is between -1 and 1. So are we interested in knowing the bounds for sine and cosine function? Because of this example 2, the squeeze theorem, evaluate this limit. And so that function, the blue function that you just saw in the previous page, was x squared sine of 1 over x. And we want to find that limit as x approaches 0. This function, x squared sine of 1 over x, does not have a value at x equal to 0, but it has a limit, and that the only way we can find it is through squeeze theorem. You've seen the sine of 1 over x. That one did not have a limit, but interestingly enough, x squared sine of 1 over x has a limit as x approaches 0. So there are homework assignment usually assigned to this type of problems. So in here, let's see, this is the let's have the parabola h of x equal to x squared, and f of x, another parabola, f of x equal to negative x squared. So this function, if you, let's see, first of all, we know that the parabola h of x as x approaches 0, the limits of that is equal to the same limit as limits of f of x as h approaches 0 and is equal to 0. So that's the thing. These two are a good candidate for squeeze theorem. Does x squared sine of 1 over x get squeezed between them? And so let's remember, sine of 1 over x, outputs of the sine function is always between -1 and 1. So the range of sine is always -1 and 1, between -1 and 1. The range of a sine function always falls between that. And so if I multiply this double inequality by x squared, and x squared is a positive value, so it doesn't change the direction of the inequality, it actually says that x squared sine of 1 over x is between negative x squared and x squared. And so it's exactly the squeeze theorem, because this function falls between these two. Therefore, since the two outer ones have a limit, then this one has to have a limit, and that limit has to be equal to the limits of the two outer one as x approaches 0. So this is how you basically show that with squeeze theorem, how to show that this function actually has a limit that is equal to 0 as x approaches 0. Now, I click here question 3. Find the limit of negative 15x sine of 1 over x plus 3 as x approaches 0. So I hope you paused the video and you thought about this. Again, The part that is going to wiggle around a lot is sine 1 over x, that multiplies x. And so I have to find two functions that squeeze this in between them. What it is that if I find, basically, if I find a limit let's see, this is going to be equal to limit of negative 15 x 1 over x x sine of 1 over x plus limit x goes to 0 of 3, right? And so that 15 can come out, it's a constant coefficient. So what I'm interested in is really finding this limit. Everything else I know what it is, and that one is 3. And if I find this limit, I multiply it by 15 and then I add 3 to it. So to find this limit now, let's observe this little information. X sine of 1 over x is between absolute value of x and negative absolute value of x, and x sine of 1 over x is going to be between x and negative absolute value of x. And so in here, because the two outer functions, limit of absolute value of x as x approaches 0 is equal to 0, and limit of negative absolute value of x is the same thing also. That means by squeeze theorem, this limit is equal to 0. Now going back to here, if this limit is equal to 0, 15 times 0 plus 3, the limit is going to be 3. And here's the function that is, this is the x sine of 1 over x, and it's squeezed between absolute value of x and negative absolute value of x. And that concludes the squeeze theorem and in this part of this section.